Log on, tune in, find out. Another good idea from Cambridge.
Last talk of the conference. Pleasure to have Sourav Chatterjee, who will tell us about large deviation principle of the Erdös-Renyi random graph.
Okay, so first let me thank the organizers for the invitation. It's been a very nice conference. So unfortunately, this topic doesn't have a lot to do with the theme of the workshop, but the pressure to submit an abstract was great. So on time, so the organizers didn't give me a chance to make a significant contribution to discrete harmonic analysis. Okay. So in this talk, we only consider finite undirected graphs without self loops or multiple edges, so just simple graphs. And there on n vertices, there are 2 to the n choose 2 such graphs. Okay. And the question is, given a property p and an integer n, roughly how many of these graphs have that property? So I'll tell you what kind of properties do we consider in this model, okay, in this work. So for instance, the property p may be that the number of triangles in the graph is bigger than t times n cubed, where t is a given constant. So there are lots of such graphs of the order e to the some constant times n squared. So we are interested in that constant. So how would you count such things? Okay. So to make any headway into this kind of question, we must assume some kind of regularity on p. So let's say p is continuous with respect to some metric or something like that. And the question now is what metric and what is the space? So what is the appropriate setup under which one can try to answer this question? So just maybe this question. It's not so clear how to count. Okay. Okay. So is the first slide okay? All right. There is another motivation, which is the original motivation. I just said the earlier thing for people who are not familiar with large deviations. So here is for the probability audience. So let G and P be Erdös-Renyi random graph on n vertices. So this is the random graph where you have n vertices and each edge is present or absent with probability p or 1 minus p, and the edges are independent. So that's the Erdös-Renyi random graph. The most widely studied model, I think, of random graphs. The number of triangles in G and P is roughly n choose 3p cubed. So that's an easy exercise. That's the expected number of triangles, and the standard deviation is of a smaller order. So that's roughly the number of triangles in this graph. So the question is, what if just by chance, let's say the number of triangles turn out to be some t times n cubed, where t is some constant bigger than p cubed over 6. Okay, so a somewhat higher number of triangles than you would expect from a normal situation. So that's the kind of question that is considered in large deviations. So what does the world look like given that some rare event happens? Okay, so what would the graph look like? Condition on this. So suppose you have more triangles than you would normally expect. Okay. So this is another kind of question, and it's basically the same as these counting questions. So it's actually sort of the same. Now, one thing that will be crucially used in this talk is this topological space of graphs, which I mentioned in the abstract. So there is this theory of limit graphs. So you have graphs embedded in some common space, and a topology on that developed by Laszlo Lovaas and co-authors, a long list of co-authors, and it's related to work on weakly exchangeable arrays due to Aldous, Hoover, and Kallenberg earlier in the probability literature. So I'm going to describe in brief this theory and some of the main results of this work. Okay. So let Gn be a sequence of simple graphs whose number of nodes tends to infinity. Let's say number of nodes is n. For every fixed simple graph H, let this denote the number of homomorphisms of H into G. Okay, number of H preserving maps from the vertex set of H into the vertex set of G. Okay. So it's not quite the number of copies of H in G. It's slightly different, but it's related. So you can get one from the other. Okay. Okay, so for instance, if H is a triangle, then this is just the number of triangles in G times 6, because there may be 6 permutations of the vertices. So this number you normalize to get the homomorphism density. So this divided by the maximum that it can be. And this actually gives the probability that a random mapping from the vertex set of the small graph H into this large graph G is a homomorphism. Okay, so that's called homomorphism density of H in G. So, so you may view it as the density of triangles. So let's just think of H as a triangle. Then TH or H comma G is just the density of triangles in this graph G. Okay. Okay. Is this definition clear?
So you're not instance of the injective?
Yeah. No. You don't insist on injective. Yeah. Okay. Okay. So suppose this homomorphism density of H in Gn, so Gn is a sequence of graphs with increasing number of nodes, tends to a limit for every fixed simple graph H. So some limit, depending on, so the density of triangles converges to some limit, density of squares tends to some other limit, and so on. Suppose this happens for every simple graph H. Then Lopez and Szegedy proved that there is a natural limit object for this sequence of graphs, which is denoted by some function in script W, where script W is a space of all measurable functions from the unit square into 0, 1, satisfying the symmetric condition, symmetric measurable functions. Okay, and conversely, every such function arises as limit of an appropriate graph sequence. So, so there is a one-to-one correspondence between graph limits and such functions. Okay. So this is a large class of functions, all measurable functions from the unit square into 0, 1, satisfying the symmetric condition. And here's the graph limit. And what is the correspondence? The correspondence is the following, that given such a function f, you can define THF as this integral. So I'll tell you the intuitive meaning of this. So THF is this integral, and a sequence of simple graphs Gn is said to converge to a function f if for every finite simple graph H, this limit is THF. Okay. So what Lovász and Szegedy proved is that if these limits exist for every H, then there is a function f so that TH is THF for all H. Okay. So that's what they proved. So there is this object that you can recover from these numbers. Okay. These numbers will determine this object. Okay. Yes.
I sort of vaguely remember something about this being invariant under permutation.
Yes, so I'll come to that. So this is the first definition about the convergence of sequences of graphs. So these are called graph limits. These functions f are called graph limits. Okay. So intuitively, what the view is that the interval 0, 1 is a continuous set of vertices, and fxy is sort of the chance of a vertex x and vertex y being connected. Okay. And this would be, if you have such a infinite random graph, this would be the density of H, homomorphism density of H in that graph. Okay, so that's how it's defined. Okay, any other questions? Okay, so here's an example. For any fixed graph H, the homomorphism density of H in this Erdös-Renyi random graph GNP converges to P to the number of edges of H, almost surely as n tends to infinity. So this is just a law of large numbers that you can prove, and almost surely requires a little more work. So this is an example. So if you, on the other hand, if f is a function that is identically equal to P on the unit square, that's a symmetric measurable function, and that satisfies this, if we just look at the definition of THF. So what this means is that this sequence of graphs G and P converges to the constant function P as n tends to infinity, okay, in this language of graph limits. Okay, that's a law of large numbers for Erdös-Renyi random graphs. Okay. this clear? Okay. Yeah, so that's what I just said. Okay, so the elements of W, this space of symmetric measurable functions from 0, 1 squared into 0, 1, they sometimes call graphons or graph limits or various names. Now, a finite simple graph G on n vertices can also be represented as a function. Okay. So this is a simple way to represent it as a function. So what you do is you break up the unit square into little subcubes of side length 1 over n, and you define the function to be identically equal to 1 on the ijth subcube or ijth cube if there is an edge between vertices I and j and 0 if not, and that's exactly what this represents. Okay. So this is one way. There are many ways. I mean, this is just one way to represent this this graph as a function. And why is the representation valid? Because you have a sequence Gn where each Gn equal to G. Okay, so you have a sequence G repeated. Then that, by the earlier definition, will converge to this function. So you can verify that it will converge to this function. So this function is one of the natural representations of G as an element of this script W. Yeah.
The function doesn't characterize entirely.
Well, you can recover the adjacency matrix from this function.
This is definition.
I didn't understand. Yeah.
With non-isomorphic graphs, you would get
different
functions.
You'll get different functions. So if you take isomorphic graphs, you get different functions, right? So we'll take care of that very soon. Okay, so note that there's a little note that allows all simple graphs to be represented as elements of a single space, because it's sort of analogous to all finite subsets of the real line, for instance, can be represented as elements of a single space, which is the space of measures on the real line. Okay, so it's sort of like that. And the question is, what is the topology on this space? Okay. Okay, so for defining topology, first let me start with the cut metric. So for any two symmetric measurable functions, Friese and Cannon define this cut distance, which is you take the integral of f minus the integral of g over rectangular subsets of the unit square. Okay, and you take supremum over all rectangular subsets. So if you allow all subsets, you would just get the L1 distance. Okay. But if you allow only rectangular subsets, you get a weaker topology, which is called the cut metric. The next step is that we introduce an equivalence relation. So this is where we identify isomorphic graphs. So we say that f is equivalent to g if f can be produced as g of sigma x, sigma y for some measure-preserving bijection sigma of 0, 1. Okay? So this is where you say that two graphs are the same if there is an isomorphism, taking one to the other, and let g tilde denote the closure of this orbit under this this metric. Okay. So these sets, so these are sets or these are equivalence classes, and these will be the elements of the space that we'll be ultimately interested in. Okay. So this quotient space is denoted by W tilde. And tau is a natural map, G to G tilde. So it takes this to this quotient, to this image. And you can define a metric, which we'll also call, we will also call it the cut metric. So delta instead of D over here between two elements f tilde and G tilde is the infimum D of the cut metric. So you take two functions and you bring them as close to each other as possible by making permutations on the coordinates. So you take two graphs and make them as close to each other as possible by making permutations, relabeling the vertices, and this is a metric on this space, and this becomes a metric space. So this is the space. This is the space of graph limits. Okay. So the earlier space that I showed, that script W, is not really the space of graph limits because there is the identifiability problem, but this space is okay. Okay, so this is the the basic setup of the theory of graph limits as developed in the last 5 or 6 years. Okay. Any questions? Okay, so this is one of the main theorems. So for any graph G, you can have its image in this quotient space. So you first take this function corresponding to this graph that I just showed, and then you consider its orbit of the orbit of this function, and that's the image of the graph in this space. So you have a sequence of graphs Gn converges to a limit f, okay, in the earlier definition. So in terms of homomorphism densities, this converges to limit f if and only if the image Gn tilde converges to f tilde in this cut metric. So that's an if and only if relation. So that's a way to metrize this this thing that I just. So you remember earlier we had sequence Gn of graphs converging to limit f, and they were, it was not in terms of a metric space and everything being the elements of the same metric space. So this is a nicer thing. So you have everything in the same space, and you can talk about sequences converging under this metric. So this is their main their first result. Okay. Sort of the first step.
Would it be possible to write down the metric delta?
Yeah. Let me see. Where are the chalks? Okay, so for any two functions f and g, you first define this fg as the supremum over all subsets of 0, 1, and you take integral over this. So you take f minus g dx dy over all rectangular sets. So that's the cut distance. And then you define this as the infimum over all measure-preserving bijections. Measure-preserving bijections. This f and g sigma, where g sigma xy is f of sigma x, sigma y. Sorry, G. Okay. Okay, so it's a very interesting question to determine what kind of functions of functional graph functions are continuous with respect to this metric. So of course this theorem tells you that subgraph densities, the homomorphism densities of various graphs, they are continuous with respect to this metric. But there are many other things that are continuous, and so there is this very nice survey of Terry Tao and Tim Austin, who is here, I think. So where you can find other things about this metric. So it's very interesting as to it has these connections with property testing in computer science and so on. So why is it useful for us? Here is the first version of our result, not in terms of large deviations, and just state in terms of counts of various graphs with given properties. So let us say you take a Borel set A tilde and W tilde. So that denotes a graph property. Okay. So any Borel subset will denote a graph property, and let A and tilde denote all graphs on n vertices which have this property. Okay, that's again a subset of this space. So this is just the number of graphs on n vertices which have this property. And let I be this this sort of entropy-like function, half u log u plus half 1 minus u log 1 minus u. And for a function or an equivalence class h tilde in this space, let I of h tilde denote the double integral of I h x y dx dy, where h is any element of this. So you have to prove that this is a proper definition. So this is the result stated in this version. This function I is well defined and lower semi-continuous on this space. And for any closed subset, the size of this fn tilde is essentially bounded by e to the minus n squared, the infimum of this function on this subset, times n squared. And if it's an open subset, then you get a lower bound. And if these two, for a given set, if the infimum is the same on the closure and as on the interior, then you get an approximate count of the number of elements that you get in that set. Okay. Okay. So this is the first version of the result that you have. It's an abstract theorem. So to count the number of graphs with a given property, you just have to take that property, consider that as a subset of this abstract space, and you have to minimize this entropy functional on that subset. Okay, and that would give you an approximate count. Okay. Any questions? So I'll soon state it in terms of large deviation theorem. So this is not exactly that. I'll do that in the next couple of slides. Okay. Okay. So coming to Erdös-Renyi graphs, so counting graphs is same as finding large deviation probabilities for Erdös-Renyi random graphs. So they are basically the same problem. So for instance, the number of graphs on n vertices satisfying a property P is just 2 to the n choose 2, the probability that Gn half satisfies P. So that is easy. And you can go the other way. If you have Gn P satisfying some property P, you can also state it in terms of counting graphs. And our main result is a large deviation principle. And this is on this slide, you will see that. So the random graph GNP induces a probability distribution on the space through the map G going to G tilde. So you have a probability distribution of space of graphs and n vertices. There is a map taking that space into this abstract space. So it induces a probability distribution on that. And here you have a parameter P. So this function has to be slightly modified. So you have IP of U to be this. And this is the entropy of a function is defined in the same way. And then you have this large deviation principle for this sequence of probability measures on this abstract space. Okay. So for every closed set, 1 over n squared log P and P of f, the lim sup is bounded by this infimum, and for every open set, the lim inf is bounded below by this infimum. Okay. That's the large deviation principle. Okay. So yes.
IP of the constant function equals to P should be 0 so that it agrees.
Yeah, it's 0. Yeah. Yes.
Do you have some variants where P is a function of n?
No. So I'll come to that. So that's one major,
Okay.
missing area.
It's
So.
very nice.
No, so that's a major shortcoming. I'll come to that. That we can only do things where P is fixed and n is going to infinity. And I would really like something where P is also going to 0 with n. Okay. Okay. So the method of proof. Just let me sketch in a couple of slides. The large deviation can be so for the weak topology. If you consider this space, so you have this abstract space. You have, let's say, you have 3 topologies: the weak topology, the strong, that is L1 topology, and in between there is this cut topology. For the weak topology, the same large deviation principle can be proved by standard techniques, what you have for large deviation theory. However, this is not very interesting. So for instance, many functions of interest are not continuous. Subgraph counts, if you consider the count of triangles or any other subgraphs other than edges, they are not continuous with respect to the weak topology. Okay, so that's why we need something stronger. And if you consider a strong topology like the L1, you cannot prove the large deviation principle. So that's too strong. So somehow this is the right one where you can do it. And this does not follow by standard methods, so I'll just sketch the proof in the next slide, and then we'll go on to applications. Okay. So here's the, okay, so to state the proof, I have to first explain Samaridy's lemma, because that's the key ingredient in the proof. Okay. So this is one of the fundamental results in modern graph theory. Let G be a simple graph of order n, vertex set V and edge set E. And for any two subsets of the vertex set, let EG of xy denote the number of xy edges of G, and let rho G of xy be the edge density. So that's the number of edges between the two subsets x and y divided by the maximum possible number of edges. So that's the edge density. And you call a pair of disjoint subsets of vertices epsilon regular if the following happens. So, okay, so the idea is that that it's epsilon regular if the edges between these two subsets look like they were distributed randomly. Okay, so that's a notion of pseudo-randomness. I mean, this is a fixed graph. I mean, there is nothing random here, but in some sense they look sort of random. So that's the idea. So let me tell what this is. So epsilon regular, if you take any two subsets of A and B of substantial size, okay, so of size bigger than epsilon times the original size of the original set, and y also has that, then the edge density between x and y is almost the same as the edge density between A and B. So that's what would happen if the edges were distributed randomly, completely, you know, that then you would take any two subsets of substantial size, the edge density between them would be almost the same as the edge density between A and B. Okay, and this is sort of a characterization of randomness of the distribution of edges between these subsets. Okay, is this definition clear? Now, a partition V0 to Vk of this set of vertices V is called an epsilon regular partition if it satisfies the following conditions. The first set has sufficiently small size, less than epsilon n. The others have all equal size, and almost all of them, so all but at most epsilon k squared of these pairs are epsilon regular. Okay, so it's a partition of the vertex set into approximately equal size clusters, so that almost all of them, the edges between almost all of them are random looking, so pseudo-random. Okay, so that's an epsilon regular partition. So Samaridy's regularity lemma says that if the graph is sufficiently large in size, okay, then there always exists such partitions. So you can partition the graph into small sets, so that into subsets, so that between the subsets things are approximately random.
So k doesn't depend on n here.
No. So here is a theorem. So you will see what k depends on. So given any epsilon, any m, there exists a capital M depending on epsilon and little m, so that every graph of order capital M or larger doesn't depend on what the order of the graph is. As long as it's sufficiently large, there is an epsilon regular partition for some k in little m and capital M. So what the lemma allows you is to choose how random these are, these edge distributions between the vk's are. So that's controlled by epsilon, and you might want at least a large number of subsets. So you might want to divide the graph into small subsets, but you might want to give a lower bound on the number of subsets that you're dividing. That's controlled by this little m. Okay. Now this capital M just depends on these two quantities. So no matter what the size is, you can always find such a partition for any graph. Okay, so that this happens. So
just to be sure to understand, in the definition of the distance,
yeah,
so the integral of s times t of f, you said that f of xy was essentially the probability that x is related to y.
yeah,
So this is the integral of f is approximately the
Yeah.
mean of rho sub g.
yeah, yeah. So exactly. I mean, what this says is that any large graph, you take any large graph, then there is a, in terms of that distance, what this says is that there is a function which is piecewise constant on rectangles, which is close to that graph in the cut metric. And the number of rectangles determines the accuracy of your approximation, essentially. It's not, the size of the graph doesn't quite matter. So it's closely related to the cut metric. Yeah, that's the edge density, right? Yeah, that's the edge density. So difference in edge densities. In the cut metric, what happens is that if you have very small sets, the edge densities may be different, but it wouldn't matter because you're just taking the integral, you're not normalizing. It's only the larger sets that will matter. Okay, so that's Samarity's lemma. It's a structured theorem for dense graphs. Okay. So how does the large deviation principle follow from Samarity's lemma? Here is the next slide. So suppose G is a fixed graph of order n with an epsilon regular partition. Let G prime be a random graph with independent edges, but not identically distributed. So you connect a vertex V to a vertex U to the vertex V with an edge if U is in Vi and V is in Vj with probability equal to the edge density. Okay. So you construct a random graph like this. You take a fixed graph, you construct a random graph, G prime. Using Samarity's lemma, what one can show, okay, using Samarity's lemma says that these edges between Vi and Vj are sort of like random. What one can show using the lemma is that this cut distance between this fixed graph G and this random graph G prime is very small. That's what you can show. If K and N are large and epsilon is small enough, you can show this. So given a graph G, you find a random graph G prime which approximates this graph, fixed graph G. Now the chance that your GNP, your Erdös-Renyi graph, is close to G prime can be computed by this probability density. This G prime is a graph with independent edges. GNP is a graph with independent edges. So you have the density of one with respect to the other. You can easily compute that, and so once you have let's say you have two probability densities f1 and f2 on the same space, and you want to compute integral f1 over a set A. So this is just f1 over f2 times f2 over A. And if you know that f1 over f2 is approximately equal to some constant c on A, then this is approximately equal to c times integral f2 over A. Okay. So you know that the chance that G prime is close to G, so this is let's say the law of G prime. The chance that, and this A is a set that of all, let's say H that are close to G, then F2 is the density of G prime. Okay, then you know that this is close to 1, and this can be approximated by a law of large numbers, so you can compute the chance that GNP is close to G. Okay, so this is a standard tilting argument. Okay, so you can have the probability density of G prime with respect to GNP, and using that and using this fact you can compute the chance that GNP is close to G. So yes.
So you don't in your G prime you don't connect edges, you don't connect vertices within the same VI.
You connect, but what happens is that if K is sufficiently large, those edges don't contribute a lot. So if you have too many parts, the edges that matter are things that are between the blocks. Okay. So there is a choice between K and epsilon that you have to make. So there is some step. So essentially, what this says is that this gives an approximation of the probability that GNP is close to G for any given graph, and then there is something that says that you can combine over all graphs to give this. So that's basically the compactness argument. So the space W tilde is compact. That's another result of Lovász and Szegedi that they proved this is a compact space, and that's not so easy to prove. But that will give you the large deviation principle. Okay, so it's very simple. Okay, any questions? Okay, so this probability density of G prime with respect to G and P, that's what gives you this entropy function. That's where it's coming from. Okay, here is another thing about conditional distributions. It's sort of technical. It just says that given that G and P has some property, what does it look like? It basically looks like the subset of all graphs with that property which have the lowest entropy. So you don't have to look at this for long. It's a thing about conditional distribution. So that's one of the things that we're interested in. Given that it has a certain number of triangles, what does the graph look like? Okay, so these are all abstract results. So this follows from, this also uses compactness. Okay, so now we are coming to applications. Okay, so far it's been all abstract theory, and it's the really interesting things come up in application. So the problem that motivated me in the beginning, so I've been thinking about this for a long time, much longer before than I was at Grant. So this was the original motivation. Let T and P be the number of triangles in the Erdös-Renyi random graph, and you want to compute this limit. Probability that T and P is bigger than 1 plus epsilon times the expected number, log, and this is the correct normalization, and if you fix P and epsilon, find this limit. Okay, so this is a very simple object, just the number of triangles in this very simple graph, and it's easy to prove central limit theorems and things like that, or laws of large numbers. How would you compute this large deviation probability? So in the sparse case, when P is tending to 0 with n, so there is a different normalization. This is not the correct one, and it was not known what is the correct normalization. So even the upper and lower bounds are not matching. So I did this last year, and then there was a paper by DeMarco and Kahn afterwards. But in the fixed P case, this was the limit. So for a certain set of P and T, okay. So this is what I managed to prove with Partode, who was a student at Berkeley, that the chance that T and P is bigger than little t times n cubed, log of that 1 over n squared converges to IP of 60 to the 1/3, where this IP is this entropy function, for a certain set of P and T, for not all P and T. Okay, so some P and some T, so some non-trivial subset, we were able to prove this limit. And the question was whether this holds for every P and T. Okay. Okay. So this was in 2009. Okay. So as it turned out, this formula is not actually true for all P and T. So that's the first surprising thing, that you have the simple looking formula and it's true in a certain range, but it's not true everywhere. So there are strange things going on. Okay, so I'll come to that gradually. So this is what we discovered. So this is a full large deviation theorem. So recall that W is a space of all symmetric measurable functions from the unit square into 0, 1. For each function, you define TF as this functional. So this is a triangle density. It's 1/6 times fxy, fyz, fzx, dx, dy, dz. And let IP of f be integral IP fxy, dx, dy. So these are just functions defined on the space. And let for each P and T, let this phi pt be the infimum of IP of f for all f satisfying TF bigger than or equal to T. So that's a variational problem. And the result is that this limit, this number of triangles in G and P bigger than T times n cubed, log of this probability divided by n squared, converges to the solution of this variational problem. Okay. And moreover, the infimum is attained over here. So that was a non-trivial thing. We were stuck on that for 6 months to prove this, because we didn't know about this work of Lovaz and Szegedi. So ultimately we did that, but then figured that they have already proved this this compactness. So this is the compactness theorem that, because in this variational problem, you take any f, you take any permutation of the f, you take a measure preserving bijection, apply it to f, it has the same property, it has the same entropy and the same number of triangles. So if you have a sequence converging, sequence attaining the infimum, if the entropy is going to the infimum value, you don't know how to reorganize it to get a limit. If you just take averages or things like that, you don't get a limit. So this reorganization, that's the proof of the compactness theorem. So what you have to do is you have to recursively apply Samaridy's lemma. So you first apply it and then you build a tower using Samarity. So that's how you construct a limit. And the limit represents the behavior of this TNP, this graph under this condition. Okay. So that's the formula for this limit. Now the question is, how do you evaluate? How do you solve this variational problem? Okay. So that's actually a challenge. We can show, as I will show you soon, we can identify regions where the variational problem is solved by constant functions, where you can find the constant, of course. And we can show there are regions where the variational problem is not solved by constant functions, but we don't know how to compute those functions. So we can show it's not constant, but we cannot solve it. We cannot explicitly solve it. We can also find limits in various directions. So as p goes to 0 or t goes to 0, we can find things like that. But an actual computation of a non-constant solution in any regime has not been possible yet. So here is what we call this replica symmetric phase, or the symmetric phase following Spain-Glass terminology. So here is the theorem. So let hp of t be this function ip 60 to the 1/3. Let h hat be the convex minorant. If t is a point where the function is equal to its convex minorant, then you can actually compute this. So this is an explicit function, and this was a limit that we found. So this earlier work with Day, where we found that this is the limit. So this falls in this region where the function is equal to its convex minorant, where you can have this formula. Moreover, for such p and t, the conditional distribution of g and p given this rare event is indistinguishable from another Erdös-Renyi graph with a slightly higher value of p. Okay. So what this says, what this says is that if you have g and p, and you have that the number of triangles is slightly larger, so the slightly larger meaning that a constant fraction larger, but the constant is not too large, then the graph continues to look like an Erdös-Renyi graph. Okay, it just behaves like an Erdös-Renyi graph. Conditional on that, you can predict the number of squares or other subgraph counts or many other properties. So it just behaves like an Erdös-Renyi graph. So that's very far away from the mean, and it's kind of surprising that it continues to behave that way. And that's why we call this replica symmetric phase. So in spin-glass's replica symmetric region is the region where things essentially behave like independent random variables. So this is where it happens. However, this result doesn't give a rate of convergence in this region. This earlier work gives an error bound of 1/√n. It was a completely different method. So this you cannot get by Samaridy's lemma. Then the next theorem is about the symmetry breaking. It shows that for any t, if p is small enough, then the distribution, then the behavior of this given this event does not resemble that of an Erdös-Renyi graph. Okay. So how is this formulated? Let C tilde denote the set of constant functions in W tilde representing all Erdös-Renyi graphs. Then for each t, there is a p prime and an epsilon, so that if p is less than p prime, then this graph with high probability is away from all Erdös-Renyi graphs with high probability. Conditional on this event. So there is a region where it just cannot look like an Erdös-Renyi graph, given that t and p is bigger than t cubed, if p is sufficiently small. Okay. Okay. Any questions?
You have this every p outside limit, or you can also put it inside probability.
I guess we can put it inside also.
You can put it.
Liminf, you have to put it as liminf. Okay. Now there is another interesting thing, which is double phase transition. So there is a P0, so that if P is less than P0, then there are two numbers T prime and T double prime. So you remember the density of triangles in an Erdös-Renyi graph is like P cubed over 6. So as long as this, so suppose you have the actual density observed is T times n cubed. So there is a region up to which you have Erdös-Renyi behavior, beyond which you do not have, but then it again comes back. If there are too many triangles, again, then it again starts behaving like Erdös-Renyi. Okay. So that's another very strange thing that you don't often see even in statistical physics models. So you start with a replica symmetric phase. You have somewhat larger number of triangles than expected. You get Erdös-Renyi behavior. Then it breaks down. And then further up, you have Erdös-Renyi behavior. Okay, so you have too many triangles, and then again you have Erdös-Renyi behavior. And this all comes from this analysis of this convex minorant and so on. And okay. Any questions about this? Okay, there is this theorem about the small p limit, which is you ask the number of triangles bigger than T times n cubed. If p is very small, okay, what would the graph look like? So you have a relatively sparse graph, p is quite tiny, and you say it has T times n cubed triangles, the T is some fixed, it's much larger. Then it would essentially look like a clique. Okay. So this limit can be evaluated, and this function represents a clique. So it's 1 at some place and 0 elsewhere. And this is a way of formalizing that. But what it essentially says is that, of course, we are interested in knowing what the graph looks like if it's not an Erdös-Renyi graph. What is a non-Erdös-Renyi behavior? So there is some indication of that. If p is very small, p is say 0.01, and you have density of triangles is a third or something like this, well, p cubed over 6, it cannot be a third, maybe a tenth, then it essentially looks like a clique. So there is a region where there are many edges almost connecting everything to everything else, and there is, okay. And this part, this is the last thing, this part you will not find in the paper that's an archive because it's new, which is about lower tails, and that's also interesting. What happens if the homomorphism density is too small? There are too few triangles in the graph. So you have GNP, and condition on the event that there is a small number of triangles. The density is much lower than expected. So one thing is we can find these limits. So if you fix u, you get some limit which you don't know, but then you can look at the behavior as u tends to 0, and this is the limit. So it's related to the chromatic number of the graph. And this is closely related to the Erdős-Stone theorem or Turan's theorem in the case of triangles from extremal graph theory. So what I can tell you what happens is that suppose you have a fixed graph H and you consider the homomorphism density of H in GNP. And if it is very small, if it's conditioned to be very small, or let's say conditioned to be exactly 0 even, then the graph looks like a complete k-partite graph where k is the chromatic number -1. So you take the complete k-partite graph with equal size partitions, and you delete randomly. You delete edges with probability 1 minus p. You delete edges from that. So that's what it looks like. Okay. So if you have an Erdős-Renyi graph which has no triangles, conditioned to have no triangles, it looks like a complete bipartite graph with n over 2 vertices on either side. And then you keep these edges with, vertices, and then you keep edges with probability p. That's what it would look like. Okay. So that also comes from this entropy minimization problem. So it's the same technique. So you have this general theorem, and you do this entropy minimization, and you can show that this sort of thing happens. I mean, in some sense, this is a version of the Erdős-Stone theorem. Okay. However, it is still true that if this homomorphism density is just a little bit below its expected value, the graph continues to look like an Erdős-Renyi graph. Okay. Again, the replica symmetric behavior comes up. So the edge density decreases, but then somehow it spreads up. So it's sort of a strange kind of behavior. Okay. Any questions about this slide? Yes.
So when you say it looks like a complete R-type graph with that chromatic number, I mean that still leaves the question of how many, what the size of the R-type class is.
No, they're equal. They're equal.
They're
So yeah, so they didn't mention that. They're equal. Yeah. Yeah. That's the thing that minimizes the entropy among everything that has zero triangles. So.
When it's very small, the number of triangles, so what happens? There's a few edges on each side.
No. So you have G and P. Let's say a fixed P.
Right.
Okay. And you condition it to have, let's say, no triangles.
So yeah, no triangles, I understand, but
Yeah.
it's very few triangles.
Very few triangles, then this is approximately equal to this in the delta metric sense, in the cut metric sense. It's approximately equal. So it gives a quantitative version of the Erdős-Stone theorem. That's what it gives. Okay, there are many open questions, even for triangle counts. So what is the set of optimal solutions when the rate function is a broken replica symmetry phase? So we basically don't know how to solve the variational problem in any other case than the. So there are these Euler-Lagrange equations that you can get out of it, and they are sometimes useful, but we couldn't solve them. Another question is the solution unique? Whether the graph, when it's non-Erdős-Renyi, whether it looks like some other graph or there is non-uniqueness. Is it possible to explicitly compute a non-trivial solution in the broken replica symmetry phase? Is it even possible to numerically evaluate or approximate a solution using a computer? That we don't know. What is the full characterization of the replica symmetric phase? So where is the phase boundary? We don't know that. And the most intriguing thing is what happens in the sparse case when P and T are both going to 0. Okay, so that's something of real interest in the sparse graph case, because many of the graphs in applications in practice that come up are sparse graphs, and you want to count those things also. So how would you do that? You need a sparse graph limit theory and a sparse similarity lemma. Okay, so there is a thanks to Ami Dembo who gave me the problem many years ago, and there is an old manuscript which provided a partial solution but was not published. So okay, that's it.
Questions?
Okay, so every graph limit gives you a model of random graphs, namely by sampling endpoints and making grid. So what do you say about it takes such a random model of random graphs and conditional number of triangles being at least something or at most something? Do you have analogous results in this situation?
Yeah, you should have. So because one version of the theorem is about counting graphs with a given property. Once you can do that, you can almost do anything with dense graphs. So you have, so basically any question about computing probabilities boils down to essentially counting things, counting the number of graphs with some given, because suppose you have some probability distribution on space of graphs, okay, and you want to sum up this thing G in some set A, okay. So then you can basically break it up into a double sum. G is an A, and so PG is approximately equal to some value U, and then U, and you just have to count the size of these sets. You have to figure out and then multiply that by U, so you can do that. Yes.
You said that you can't determine the speed of convergence this way.
What?
You said that you can't determine the speed of convergence this way. You think it's actually slower than?
So one thing I forgot to mention here. This theory has also been applied. So I did it recently with a work in a work with Percy Diaconis on analyzing exponential random graphs. So these are models of random graphs that are used in practice by social networks people. So we can explicitly solve these exponential random graph models in many situations. Now there, Percy got a student to do simulations and check whether our results match, and they are close for n equal to 30. So the convergence should be pretty fast. But Samarity's lemma, with Samarity's lemma, you have no hope of getting 1 over log star, and if you're satisfied with that, then it's okay. But there is no way to get a rate of convergence by this technique. So this earlier work with there I used different technique for the replica symmetric phase, where we could get a 1 over root n rate of convergence. But that doesn't apply to the full situation. But I think the rate of convergence is pretty good. Yes.
But there is this analytic version of Samarity's lemma which has much better bounds. It's a weaker thing, but I mean, how close is it to what you need?
So do you mean the one with 2 to the epsilon squared instead of 2 to the 2 to the 2?
Yeah, that's what I think.
Okay, 2 to the epsilon squared will give you 1 over square root log n.
But it works in your theorem.
It should work. I mean, it should. The weak lemma, that should work. Although we didn't go about doing that. I mean, but I believe it should work. I mean, the proof involves a strong Samarity lemma, the proofs that we have in our paper. But I'm pretty sure it should work.
So there's no further question. Let's thank Sourav again.